In this recording, we're going to review Units 7, 8, and 9. Okay, Unit 7 was having to do with exponential functions, Unit 8 had to do with logarithmic functions, and Unit 9 was sequences in series. So the first question we're going to look at is a pretty unusual looking equation that has x up in the exponent. So in order to work a question like this out that has x in both exponents, we could try to get a common base that we could convert 0.5 and 8 both into. So it turns out in this case the number 2 can be written for a base to make a 0.5. So 2 to the negative 1. All right, you need a negative base to make fractions or decimals. And still the exponent of 3x plus 2 is remainder. And then for 8, that can be written as 2 cubed. Okay? So 2 cubed is 8, so I'm writing something that's equivalent. I haven't changed the value of either side, right? I've just rewritten it in another form. And now I can apply laws of exponents, power property of exponents, as I distribute the exponent. Okay, and that's the biggest mistake students will make here once they have the common base, is forgetting to distribute the exponent. So really concentrate on that. Don't make that mistake. Okay, so it's 15x minus 12. From here, because the exponents are the same, because the bases are the same, the exponents must be the same, because they're the corresponding parts of this equivalent, equation. So we can set the exponents equal and then do the math. Go ahead and solve that out. Play the recording when you're ready. Okay, so hopefully you got all the x's on one side and all the numbers on the other side. And when you divide it, the simplest form of that answer is 5 over 9. Okay, this next question is a tough one as well. We are given 2 points on an exponential curve. So we can think of this as like, that's an x, and that's a y, and that's an x, and that's a y, right? So turns out we can put them both into this form and then start to try to figure out what a and b could be. So I'm going to first write f of x equals a times b to the x, and then I'm just going to sub in the x and the y from that first point. A and b are unknown. Okay, so something like that. And then my second point. Okay, with a situation like this, what I can do is divide one equation by the other. I'm going to divide in such a way that the a's divide out, and I would like the larger exponent to be in the numerator. Okay, what allows me to do that is both sides are equal here, right? That's what the equation says, what the equal sign says. So I can divide one side by 102.4, the other side by a times b squared, and I'm really dividing by the same thing. Here's the point. The a's divide out. So now at least I'm just dealing with one variable. And with the b's, we can use our quotient property, b to the 4th over b squared. Well, that just leaves me with a b squared. Then you could do some math on your calculator. Turns out it works out to be 0.64. Rarely in life will it work out to be quite so clean, but we made up these problems so that the b value here is going to work out being a nice rational number. Okay, when we square root both sides to undo the squaring, turns out that b is going to equal 0.08. I guess it's really the absolute value of b, or just 0.8. And of course b is just positive 8. We can't have a negative base. All right, so that's good news. We got that piece. Now we're going to find out what's a. So you can use either one of these equations, whichever one looks easier to you. I kind of like the top one. I'd rather deal with a square than a fourth power. So I'm going to start to write it out. I don't know what a is, so I'll leave it as a. I do know what b is. Now just do the math and find out what a is. So now I can write the function. Okay, a is 160, b is 0.8. And what I should do is I should put this into my calculator and check that when x is 2 and when x is 4, those are the corresponding y values. Okay, but part B asks me to evaluate it when x is 10. So think about what to do and then work that out and play the recording when you're ready. Okay, so something like that just simply means find the y value when x is 10. Okay, and that works out to be 17.18 to the nearest hundredth place. Okay, the next question we're going to look at is number 5 on the next page. Pretty challenging question here. In fact, they're all challenging in this exponential unit, I think. So it's worthwhile that we're going through them. Why don't you take a second to read through the question and then try to wrap your head around maybe any answers you could eliminate or what possibly we could do to resolve this question, and play the recording. Okay, this one asks us in terms of the monthly rate of decay, whereas here we have t representing the number of years since the study began. So t is still the number of years. Okay, that hasn't changed. That can't change. But we need to represent it in terms of the monthly rate of decay. And so that's really the key here, is getting that monthly rate of decay. So I guess you would maybe look at these first couple choices and say, those are absurd. Can't be those, right? And maybe these last couple you'd say, well, if t is years, you can't have monthly rate raised to the year power, so maybe that's out of there too. So maybe right away we know that 4 is the only reasonable choice, but let's talk about why that is in case it's not a multiple choice. So the way to get the monthly rate of decay is to raise the yearly rate to 1/12. Okay? When you do that math on your calculator, it turns out to be 0.995. And when we look at this choice here, it has that monthly rate of decay, and every year, which is t, we're getting 12 of them. Okay, so really it's equivalent, because when I raise this number here to the 12t power, the 1/12 and the 12 divide to 1, and I just have the 0.94 to the t, right? So it makes sense that that could be. So I'll just get rid of that work there. I'll just make a little note here. So since the rate of decay is in terms of months, not like years like it was up here, the exponent must be a number of months. And so those always have to correspond. Let's look at number 6. Number 6 is very similar to one we worked out earlier. It's just that the numbers aren't going to come out quite as cleanly. So we're going to ask you to round the a value to the nearest integer, the b value to the nearest 10,000th. So why don't you read the information that's provided here, see what you know, what you can try to figure out, and play the recording. Okay, so hopefully you discipline yourself to do something with this, not just watch me do it. And you have a time and distance pair, and another time and distance pair, and they're both going to be represented by this exponential function. A times b to the x. So therefore, we have an x and a y. And then we have another x, and it's, I'm sorry, I got messed up there, an x, and that 7 feet is really a y value. Okay. So once those are paired, we can make substitutions. Let's try the first one. A and B are unknown. That's what we're trying to find. The initial value, which is that A, and then the multiplier, which is the B. So the other equation can be written involving 5 seconds and 7 feet. So if you recall, what we did before was try to solve for A and B. Why don't, if you got this far, why don't you see if you can take it from here? We've done one like this earlier. See if you can take it from here, finding out what A and B are. All right, so hopefully you worked those out and you did some division. You might wonder, well, which one do you put on the numerator and which one are you dividing by? I prefer for the b's exponent to be a positive number. So I'm going to put the 7 equals a times b to the 5th and divide that by the other equation. So at this point, it's going to be pretty straightforward. It's just that 7 divided by 65 doesn't come out so cleanly. So we'd like to use as many decimal places as our calculator has. Okay, we don't want to cut this short. And that's equal to the a's divide out nicely. B to the 5th over b squared results in a b cubed. So we want to undo that cubing by cube rooting. And so we need a calculator to get the cube root of that number. And it asks us to round, so we get b to the 10,000ths. So we're going to need 4 decimal places. So it's about 0.4758. Once we have that, we're in good shape. We can use either of these forms. Again, I kind of like the one with the square, easier numbers to work with. A is unknown, but B we're approximating to be 4758. And again, it's to the square, the second power, because I'm using this form of the function, subbing in that y and that x. Now we just do the math. Turns out when I do that, on the right side, that number squared is 0.226386. Again, I'm not trying to shortchange any of these numbers. Keep as much precision as possible all the way through and just round your final answer. So when we divide, I get an A value. That's about 287. So let's write that in a final form. Now if we were to check this with our calculator, we should hopefully at x equals 2 see something pretty close to 65, and when x equals 5 see something pretty close to 7, although it may not be exactly the same because of the rounding that took place here. Okay, the next question we're going to look at is number 8. Unlike the other ones, this one's pretty straightforward. It's a transformations question. So play around with that one and play the recording when you're ready. Okay, so hopefully you recognized this has some sort of a shift. Is it a log or a exponential function? Well, it would not be an exponential function. Those would look more like this, right? So we don't have that behavior. So those are out. Log base 4, log base 2. Well, either way, they would both have an asymptote of the y-axis. And this one has a shift to the right of 2 units. So the only one that makes sense of shift to the right 2 units is that one. I could take a particular point, like that right there. Looks like 3, 0, and I could substitute that in and see if it makes a true statement. So y equal, or I guess I should say, I'm going to sub in 3, 0. I got to do 0 equals log base 4, and when I sub in 3 for x, I get here a 1. So log base 4 of 1 equals 0. And if you remember, we can write this as an exponential function by doing 4 to the 0, right? A log is an exponent, equals 1. And of course, that is 1 equals 1, so it checks out. Okay, nothing more on that page. Next question we'll look at is number 11. So this question, why don't you read through it and see what's asked for you and play the recording when you're ready. All right, so for this one, we're given a y value, and we want to know what's the value of x, so we'll make it true. So we're going to substitute in 90, and then do the math. Okay, x is pretty deeply buried in this equation. There's several things we're going to need to do to isolate it. Hopefully you would recognize that we have an unknown exponent. You're going to need to use logs. Okay, logarithms are useful to solve for an unknown exponent, but don't use them yet. First, isolate the exponential function. Undo that plus 75. Undo that division by 50. Now we're in pretty good shape, as long as we know about logs. And we may not, right? We may have forgotten. You might be saying, I don't remember anything about logs. Here's what you need to know. A log is an exponent, right? So I can write this in logarithmic form. This exponent of x has a base of 0.92. So when we write log form, log has a base. The base is the same, 0.92. The log is the exponent, so leave some space here and say equals what the exponent was. So that's x. And then this is called the argument of the log, 0.3. Now it's a calculator question. I can go to my calculator and evaluate this. So I go to my calculator, I do alpha, window, got choice 5, and I can put in 0.92. And it comes out to the nearest hundredth to be 14.44. Okay, again, that could be checked. We could sub that back in and confirm that we're pretty close. Okay, we have a nice application question here. Why don't you read this and write down anything you know, anything you can remember, or anything you can pull from this, find out what we're trying to find out, then play the recording when you're ready. Okay, so for this one, we have two functions, a of x and b of x. Well, I guess it should be in terms of n. Let me back up and call it a of n and b of n. Just because it says here n years, so I'll be consistent with that, b of n. So the first function has a $45 initial amount. Sorry, $4,500 initial amount, big difference there. And then it's 1 plus the rate, right? So 1.026. Right? That's how we represent 26% raised to the n power. The second one says it's going to be compounded monthly, the b of n formula. They're not going to give him just one time a year. They're going to give it to him every month. And actually that works better for him because that money makes money, right? The interest compounds. So we have 1 plus but you're going to get a 12th of that rate. So like at the end of January, I got to get this right. Got to get that decimal slid over. Let me try again with that. 0.025 divided by 12. All right. So he's going to get a 12th in January, a 12th in February, etc. But he's going to get it 12 times every year. So to the 12n exponent. There are our two functions. The second part, why don't you read through and see what you need to do for that second part. Okay, so hopefully you recognize, hey, all I need to do is evaluate what it's going to be after 5 years. So go ahead and work both those out. Okay, so even though it would work better if you were getting the same interest rate and were getting it compounded more frequently, having that extra 1/10 of 1% helps him out more in the long run than getting it compounded monthly. So the question is, how much more? We just need to do the subtraction here. So when you do the subtraction, it works out to be $17.71 more in option A. Final question says, okay, how long is it going to take for his money to double? So would you think about that one for a little bit and then play the recording when you've got it worked out or you need some help? Okay, so hopefully you thought about that. You're not just writing down what I'm writing. Use your brain here. Let yourself think. What's double that investment going to be? Okay, so we started with $4,500. It's going to get him up to $9,000 if he doubles it. And using our initial, the option A, it's going to look like this. Or the simpler form. And I have to solve for an unknown exponent, so hopefully it's coming back to you, right? Got to solve for that unknown exponent with logs. Can't put it into log form until we have it, the exponential expression isolated. So divide. And no surprise, it comes out to be 2. Now I just need to work this out with logs. So think about what the log form of this exponential equation would be, and then play that recording when you're ready. Okay, so hopefully you're getting it a little bit more now. This is a base of 0.026, so a log needs a base. The log is the exponent, so it's going to be equal to n, and then 2 is the argument of the log. This becomes a calculator problem. So if you have a calculator, pop that into the calculator, see what comes out. So to the nearest tenth of a year, 27.0. And we are actually going to put that 0.0 on there. You might say, well, does it really matter? It matters. That gives us some information about the fact that when it rounds to the 10th, the next number after it was a 0. So all right, so now we're going to switch gears and start talking about our last unit from last year, which was sequences and series. And I want to bring something to your attention before we dive in and look at that. You have your Common Core reference sheet, and that's going to be part of your Regents exam. There's some stuff on there that's relevant. You got your Pythagorean theorem, but you already know that. Your quadratic formula, you already know that. You've got your radian and degree conversions, which are handy if, that was useful. This isn't going to be super handy, this exponential growth and decay form, but it's there. But these formulas for arithmetic and geometric sequences and your geometric series are going to be pretty useful. So let's just review them. If you want to find the nth term of an arithmetic sequence, it can be found by knowing your first term, the number of terms you have minus 1 times the common difference, what's being added or subtracted each time. Your geometric sequence, remember, those are your multiplying type of sequences. Okay, so any term can be found by your first term times the common ratio, what we're multiplying by each time, okay, raised to the n minus 1 power. And then your geometric series, a series is like a sum of all the terms in a geometric sequence. And again, you're familiar with the first term and the common ratio. We represent the sum with that s. So the first question we're going to look at in this one is number 4. Remember, this looks pretty complicated. This is a sigma. It's basically like a little loop, a little algorithm to work out this particular summation. So we start with the number 1 as a value of k. We're going to keep counting 1, 2, 3, 4, and we stop when we reach the final value of k up on the top of the sigma. So it's just sub in 1 into this formula. So 1 squared plus 3 times 1 would be 4. And 2 squared, which is 4, plus 3 times 2, so 4 plus 6, that's 10. Hopefully it's not messing you up that I'm kind of doing this in my head here. Now sub in a 3, work it out, sub in a 4, write those numbers down. Okay, so hopefully it worked out. When you sub in the 3 squared plus 3, so it's 9 plus 9, so it's 18. And then 4, so 16 plus 12, we end up with a 28. All right, and that says add them all up, and that's your final value of 60. So that's how you work out a summation. The next one we're going to look at is number 6. So we have here a series. It does not tell us whether it's arithmetic or geometric. So that's going to be our first task, is to find out if these terms have an adding pattern or a multiplying pattern. I think we can recognize pretty quick it's an adding pattern, so that makes it arithmetic. So if it's an arithmetic sequence, or in this case an arithmetic series, we can find something about the particular terms using our arithmetic sequence formula. All right, so let's write some facts we know over on the side here. We've got a sub n. Well, I guess we could first start out by writing out the formula from our reference sheet. A sub n equals a sub 1 plus n minus 1 times d, the common difference. So we're going to need to know all of these things. And some of them we can just pull out. Okay, so a sub n would be the final term. Okay, so that's 138, or the nth term. N, well, we don't know. I mean, we really could find out, right? It wouldn't be impossible. If you're on your exam and you need to know which term this is, you can keep adding by 5 and you'll eventually get there, right? You just need to be precise. Let's pretend we don't know that, because we don't. The first term, well, that's 8. And then the common difference is what we're adding on each time. So plus 5, it's going to be called 5. Okay, so we're trying to find the number of terms. That would be n. So we can just make substitutions in here and work it out. Again, this is not the only way to do this, but at this point we can just do the math. N equals 27, we know that that's the 27th term. Now to find the sum of this series, well, they didn't provide us with that formula, all right? So turns out that formula for an arithmetic series looks like this. The sum of the first n terms is n over 2 times the first term and the last term, the nth term. So I don't know if that means that this wouldn't come up on the Regents because they didn't give us the formula, if that's not being emphasized, but let's know it anyway. You can basically think of it as the average. We're adding up the first and the last, dividing by 2, so that's the average of the first and the last, and then we're multiplying it by how many terms we have. So 27 is the number of terms we just found out there are. First, divide by 2. First term was 8. Last term was 38. Do that math and it comes out to be 1,971. Now, if you're saying, couldn't I have just kept adding on 5 and adding up all those numbers? You sure could. And if you were precise, you'd come up with that answer. But isn't this clean, in terms of not having to do a whole lot of work if we happen to know that? The next question we're going to look at is number 7. We have a sequence here, and I want you to just look this sequence over and see what kind of pattern you see emerging. So hopefully you recognize that the numerator stays at 18, but the denominator gets multiplied by 5 each time. So it went from, I guess you could think of this as like over a 1, right? And then times 5, times 5, times 5. So it's 1/5 as big as it was before. The value of r, that's what we're always trying to find here. What's the ratio? What's the common ratio? And technically, if you can't figure it out, the way to find the common ratio is to take a particular term, 18/5, and divide it by the previous term. So you could take 18/5 divided by 18, and you can just divide across if you like. 18 over 18 is 1. 5 divided by 1 is 5. All right? So 1/5. So we know r is 1/5. We know a sub 1 is 18. So to write a recursive formula or model, looks something like this. A recursive formula says you need to know your first term, which is 18. And then you need to know what you need to do to that term to get the next term. So what we're going to say is take your previous term, a sub n minus 1, and multiply it by 1/5. Okay, so this notation right here refers to the previous term. Because if you'll remember, the subscript tells us which term numbers. That's a sub 1, a sub 2, that's why we say it, a sub 3, a sub 4. So if I know the first term and I want to find the second term, what that means is take the previous term, so that would be a sub 2 minus 1, that one, and then times 1/5. So that's our formula right here. It needs both parts. You have to have the first term stated and then the pattern to get to the next term. The explicit formula, well, remember we talked about earlier, you have your New York State Common Core reference sheet here. Well, there's an explicit formula for a geometric sequence that consists of the first term times, let me get that out of the way, times the common ratio to the n minus 1 power. So back over here, a sub n equals the first term times the common ratio to the n minus 1 power. That's our explicit formula. It allows us to jump, like if I wanted to jump to the 12th term, I could do that really easily just subbing in 12 for n. Finally, it says, okay, find the sum of the first 10 terms, s sub n. Well, that's going to necessitate the formula, but we have it over here again. Okay? So the formula says your first term minus the product of your first term times r to the n power all over 1 minus r. We'll just write that formula in our margin. Okay, sometimes you'll see this formula with the a sub 1 factored out. But either way, it's going to work out to be the same. So first term, why don't you, you know how to do this. You've got a formula here, you've got values. Go ahead and plug in all those values and evaluate it, please. Okay, so hopefully you paused and worked that out. Okay, n is 10 here. And this just becomes a calculator problem. You put all that in your calculator, it's going to come out 22.50 if we're to round to the nearest hundredth. All right, guys, last problem we're going to look at is on your eMath Unit 5 quiz. We're going to go down and look at question number 4. Looks pretty complicated, this question number 4. So why don't you read all the information that you have, figure out what it is you're trying to find, play the recording when you're ready. Okay, I know it's been a long video, but if you have not paused this and tried to figure this out on your own, you're depriving yourself of an opportunity to learn. So please pause and figure this out as far as you can. Okay. We've got a formula here that's provided, and we've got a lot of information. We've got the loan amount, yearly interest rate of 5%, and that there's 48 months. Okay, now we have to determine each of these values. R is the monthly interest rate. So this is where it gets a tiny bit tricky. Yearly interest rate versus monthly interest rate. All right, so if I wanted to find the monthly interest rate given the yearly interest rate, what I need to do is divide 0.05 by 12. Okay, so that's how much interest we're giving out each month. All right. Well, in that case, proceed to sub in. So 0.05 divided by 12 multiplied by P. P is the loan amount. That's going to be $15,000. The denominator is 1 minus 1 plus R. Again, R is this rate. Raised to the exponent. Get another set of parentheses here. Raised to the exponent negative 48 because there were 48 pay periods, 48 months. That looks really complicated, but guess what? It's very doable on a calculator. So if you have access to a calculator, meticulously make your screen look exactly like your paper does, with all the parentheses and the fractions within the numerator and denominator. I'll illustrate that real quick. Okay, I did leave off parentheses around the fraction and down here the fraction. Hopefully that didn't mess you up too bad. And then when we evaluate it, 345.44 looks like that is a choice. Or we're feeling pretty good about choice number 4. Thanks for watching.